Hello and welcome to this virtual IEEE VR workshop talk. I'm Thomas Rausch from the Technical University of Vienna. This is a larger collaboration between TU Wien, VRBIS, Columbia University and Cognitive XR, which is an academic spin-off we're in the process of founding, of which I'm also the technical lead. So we're building a platform for smart city-scale cognitive assistance applications, and I first want to talk a bit about cognitive assistance applications in an urban context. So imagine you're riding your bike through the city and the smart glasses you're wearing show you an overlay with data from your navigation system. But it can also display a silhouette of the car that's about to turn the corner that isn't even in your field of view yet. Or imagine you're one of the millions of people worldwide who suffer from corneal disease, where an AR wearable with object detection can help you find your favorite yogurt in the supermarket. Or think of people with cognitive impairments that struggle to interpret emotional responses. Here you can see a prototype we've built that does AI-based emotion detection on a video feed, which could be used for an AR application. So there are lots of other use cases like this, and there's already substantial research in the area. But what I want to highlight is that these wearable cognitive augmentation applications sit on two pillars, namely AI-based video analytics, so analyzing the video feed from the glasses. Obviously for interactive applications that needs to happen in real time, so using cloud-based solutions or the on-device capabilities is often out of the question. And the second thing is real-time access to sensory data from the environment, such as cars being tracked, road conditions, things like that. And the foundation for these two pillars, which is what our platform aims to enable, is really this emerging paradigm of edge computing. Edge computing has its own research community and has lots of different application areas, but it plays a fundamental role for mixed reality systems. Here's Ken Perlin talking about edge computers in his keynote at the Visual Computing Trends Day a couple of years ago. And here you can see the AR device is connected via low latency 5G connection to proximate compute resource that has a GPU. And this can facilitate the types of interactive applications that we've been talking about. And our project, Cognitive AR, is all about the question of how to scale this up to a citywide system. So in our vision, edge nodes are distributed throughout the city, which contain embedded AI hardware and sensors for tracking objects. Our platform handles the runtime management of these distributed resources and the applications running on top of the infrastructure. And we provide client software that abstracts the communication layer and makes it easy for AR developers to access the system in a transparent way. For the infrastructure, we're building on existing smart city projects and ideas from these projects. So, for example, the Array of Things, which is just a box of sensors, camera, and some single-board computers distributed throughout the city, connected via mobile internet. And we expand on this idea to include what we call multi-purpose edge computer clusters, which is just a federation of small form factor computers with different computing capabilities, and our platform hides this federation, makes it look like a single computer. So far, we have a design for the architecture and a few prototypes for individual components. You can find the details in the paper. For the rest of the talk, I want to demo what we have so far for these two pillars that I talked about earlier. And one part of that is the sensory data from the environment, specifically the tracking of objects. And for this, we've been developing a system we call the CyberPhysical Object Positioning, or CPOP. Here you can see a prototype of how you can use CPOP to track the 3D position of an object. The top left is what the tracking camera sees, and the bottom left is what the user wearing the headset sees. In this prototype, we use a regular webcam attached to an NVIDIA Jetson Xavier, which is a small edge computer with a GPU. That does the object detection, depth estimation, and with the camera calibration does the translation into 3D position. It sends positional updates via Wi-Fi to the AR device, and the device is anchored to a common origin, which allows us to display the bounding box. So the AR device isn't doing any tracking, it's just receiving the data from the environment in real time and doing something useful with it. For offloading AI video analytics from edge devices to edge computers, we're developing a system called CogStream that enables the access to various types of AI services, for example, emotion detection. First, the devices engage in a negotiation about the optimal streaming configuration, for example, the frame rate, compression quality, or which device does specific frame transformations. And then the edge computer simply returns the results from the AI model inferencing frame by frame. We have some results in the paper that demonstrate that it works and how important edge computing is for interactive applications. Cloud-based solutions like Azure Cognitive Services just have too much latency, but there's already lots of existing research that goes into this performance aspect in depth. So this is what we have so far. Building this type of platform has lots of challenges that we're going to tackle in subsequent research. For example, dealing with uncertainties in object tracking and reconciling data from multiple sources. When we do AI-based video analytics for things like retail use cases, we have highly domain-specific models. So if we want transparent access to them, the platform needs to know, based on the context it's operating in, which one to use. In a citywide infrastructure, you have the issue of handing off communication from one node to the other while the user moves around. It's not clear how well that will work. LTE base station handoffs, for example, incur several seconds of latency, so that's not ideal. And also the operationalization aspect. So for example, how to streamline the calibrations of cameras if you have thousands of them. And the huge issue, of course, when cameras are involved is privacy, but that is a topic for a separate talk. So this concludes my presentation. If you're interested in our project, please reach out. You can find Cognitive XR on the web, or feel free to contact me directly.